Our next speaker is Giacomo Fenzi. Giacomo is a PhD student in the COMPSEC lab at EPFL. His research is focused on proof systems and especially on how to make CK stars that are theoretically and completely efficient from post-quantum cryptographic primitives. Last year, Giacomo and his co-authors actually won the Best Paper Award at Crypto for their work on STIR, which is an interactive oracle proof of proximity construction, which can be used to construct efficient snarks. So in line with our overarching workshop theme this year, Giacomo will tell us about how to make advanced cryptography practical. In more detail, he's going to talk about the applications of proof-carrying data, in particular to aggregation of post-quantum signatures, as well as his recent work on constructing proof-carrying data from accumulation. Take it away, Giacomo.
Hey, everyone, and thank you, Matilda, for the very kind words. So today I'm going to talk about WARP, which is our new work on linear time accumulation scheme. So this is joint work with Benedict Funz, Alessandro Chiesa, and William Wang. So being a workshop about cryptographic application, I decided that instead of focusing exactly on the construction, I'll start by talking a bit more broadly on why I think accumulation schemes are nice primitives to work on, and some applications that benefit directly from them. And so we'll start with this, then we'll work our way to why accumulation schemes are useful, and then we'll see whether we have time to get to the construction. And the application that I want to talk about is that of the aggregation of post-quantum signature. And the context in which it is helpful is within the consensus mechanism of Ethereum. So, for context, Ethereum is this big, by now, decentralized blockchain, and each blockchain relies on a consensus mechanism. This is where the validators in the network agree on a new state, which will then publish to the blockchain. In order to actually make the finality process as fast as possible, the Ethereum consensus of Ethereum is more complex than all in other cases. So in fact, the strategy for which nodes reach consensus relies on a few steps. The first step is that a subcommittee is chosen. So you have the entire set of validators, and then out of these, a random subset of validators, this committee gets chosen. And these are the ones that decide the state. Once they agree on this state, each of them generates a signature of the state as a way to attest that this is the state that they've chosen. Now, while this validator is a smaller set than the entire set of validators, these are still quite a bit. You can think of them to be in the order of like 10,000 validators, give or take. So you can imagine that just publishing all these signatures to the network would be like very costly. The network is very globally distributed. It's hard to actually do this thing. So there's a step in the middle to try to avoid having to send it to the network, and that is basically an aggregator. So the aggregator takes these many signatures, these 10,000 signatures, and aggregates them into a single one. The aggregated signature is then published to the network, and the remaining validators, the larger validator set, ends up verifying these aggregated signatures. So, okay, so this is the overall blueprint of why post-quantum signature aggregation is relevant for Ethereum. Now, let's see what are the requirements that we want for this system. So the first thing is that the aggregator should be very efficient. The aggregator in reality is one of the validators, so we want the memory requirement, the other requirement, to be as little as possible, because we want to lower the barrier of entry of nodes into the network. Next, we want the aggregated signature to be as small as possible, because remember, we need to propagate this to a globally relevant network. Finally, each of the million-plus validators need to execute the signature verification. So each computation repeated 1 million times is very expensive, so let's try to make it as cheap as possible for the entire network. The current solution that Ethereum is using at the moment is via signatures, which have great aggregation properties. They're best on elliptic curves and pairings, they're great, you can really just squash them together into single signatures. So this matches all the requirements Ethereum has. The issue is that we know that elliptic curves don't play very well in the post-quantum world. And since Ethereum is a very globally distributed network, updates are hard. So Ethereum is trying to get ahead of the game, and is trying to figure out how to transition to post-quantum alternatives. And currently, the main idea of what we're trying to do is to actually use hash-based signatures as a replacement. So In particular, the current proposal is to use a hash-based variant of internet signatures as the signature used by the validators. The problem is that now you have a bunch of hash functions which basically just look like Merkle trees, in a sense. And so a question really comes, how can we recover this system with these hash-based signatures? Now we don't have any homomorphism, so aggregating is very hard. Okay, so we're going to try to see how accumulation scheme gives us a way to tackle this problem and with interesting parameter trade-offs. So the first idea that you might have is to just use a post-quantum snark to aggregate signatures. So pick your favorite post-quantum snark. I have a favorite that if you want you can hear more about at 9 o'clock in the proof system track. And now we're going to take the same setting as before, and we're going to try to see how we can fit the post-quantum snark into this setting. So the aggregator receives again the list of signatures, and now he runs the prover of the argument to prove that all these signature verification succeeded. The new proof is then propagated to the network, and the validators end up checking whether this proof is valid. Okay, this is a strawman approach. What are the good things and what are the bad things? Well, first of all, if the signature is post-quantum secure, sorry, if the argument is post-quantum secure, this system is not vulnerable to quantum attacks. These are succinct arguments, so both the size of the proof and the verification are relatively small compared to the computation being proven. So you get like a gain to compare to the initial state, to the initial approach of just sending all the signatures. The drawback is that both the proof size and the aggregator end up having a dependence on the number of signatures. And of this, the most salient requirement that we're breaking is the fact that we want the aggregator to actually have like a small memory requirements. Snarks have a large overhead in terms of like how much memory is needed. So you can think that this aggregator would maybe need hundreds of gigabytes of memory, which is simply not tenable. So we would want something to improve on these things by especially removing the memory things. The tool which I'm going to reach for in order to solve this is a very beautiful idea by Val in 2008, and it is that of incrementally verifiable computation. So what's the idea? Well, in incrementally verifiable computation, you're trying to prove very repeated computation. So you have like some f, which you can think of it as a transition function, and ideally you would want to prove that many applications of f reach some result. The way that IBC aims to do this is by splitting the computation into many transitions and then proving each one of them piecewise, individually. To map it back to our concept of signature aggregation, you can think of like the transition function to be like maintained, so this is way too small. So you can think of it as being like maintaining the current, all the previous signature aggregation and then adding on that the verification of the next signature. So functionality, how does it look like? Well, you start the prover of the IBC, start with some input, and then from the input generates the next input and a proof. And this continues for some steps. And the verifier can then just verify the final input and proof pair, and this will attest to the validity of the entire computation. What are the good things about this system? Well, first of all, the IBC prover never has to see the entire computation. He only sees it piecewise. So in theory, you could have a memory costs which are independent from T. This notion can also be generalized to something called proof carrying data, in which instead of considering this computation which is an line, you consider a more general directed graph. This is quite nice because in practice it allows us to reduce latency. Okay, so let's see how we can take this incrementally verifiable computation and apply it to the previous diagram that we had. So, this is the blueprint that we're going to look at. So, we're going to take what we had before, and we're going to take a post-quantum secure IBC scheme. And we're just going to apply it in the aggregator instead of like the snark. Okay, now the proof will be propagated as before, and the validator of the network will just run the IBC verifier. Okay, this is a nice little surgery that we have done. What does it give us in practice? Well, if the IBC is post-quantum secure, we still get post-quantum security. If the proof size is now independent from T, so this is better than before where we might have had some dependency on T. The aggregator is cheap, the memory cost can be much significantly reduced by using this approach, and you still retain the cheap verification that you had beforehand. So this seems to meet all our functional requirements. which is wonderful. So the natural question that kicks the can down the road is, where can I get LVC? Where can I get this beautiful primitive? Well, traditionally the way that this was done is by something called recursive recomposition. It was the original setting in which Valiant envisioned IVC being constructed. What's the idea? Well, you take a star and then you use it to build IVC. So these are these beautiful black boxes are the interfaces of the IVC that we talked before. Roughly use the star to prove that the transition was correctly executed, and further that the verifier of the snark would have accepted the previous proof. The verifier of the IVC then simply checks that this proof is a valid proof. I'm skipping a lot of details here because you have to actually have pre-processing. There are some ways to actually implement the recursion which are a bit complex, but I think that for the intuition of the slide, this is more than enough. Okay, what are the positives and the negatives of this approach? So, the positive is that if the snark is post-quantum, you get post-quantum IVC. You get chip verification because at the end the proof is a snark proof. And you get both the independencies from T that we wanted. What's the negative? Well, now, intuitively, the best you could hope for an IVC is to just prove the transition function, because that is what we're trying to do. In this case, you can see that the snark prover actually has more cost than that. It needs to prove both the transition function and the verifier of the argument. This difference is called the recursive overhead. And if you think about the application that we were considering, signature aggregation, verifying a signature is much simpler than verifying a full snark in most cases. So this recursive overhead is quite large. So this is a good starting point, but we can aim to improve it. And the tool that we're going to use that is finally the centerpiece of the show, which is accumulation schemes. So the way you should think about accumulation schemes, this is a lightweight tool in which you can take many checks and to patch them into a single check, which is we call an accumulator. More formally, you can think of that you have some relation that you care about. Think of this as being multilinear polynomial evaluation, throughput SAT, R1CS, your favorite NP-complete relation, say. And you have many checks that you wanna verify. And you wanna put them all into an accumulator act. So there will be an accumulation prover, which takes as an input this list of relation, and also will let it take other accumulators, which might themselves be the result of accumulating other instance witness pairs into them. The accumulation prover will take all of these things and then compress it to a single accumulator and then generate a proof that attests to the validity of this accumulation. So I'm making a distinction because actually the verifier in an accumulation scheme is split into two things. One of them is the accumulation verifier, whose only role is to actually check that this process of taking the instance witness pairs and the accumulation and putting it into the accumulator was done correctly by using this proof. And then you have a decider whose only job is to decide whether this accumulator is valid. So we're splitting this in two parts. What are the soundness requirements that we want for the scheme? Well, we want if both the verifier verify this transition to be successful, and if the decider accepted the final accumulator, then, unless with cryptographically small primitive probability, all the accumulated instance pairs will have been in the relation, and the decider run on the input accumulator will have accepted. You can think of this second part to actually also check the previous instance witness pair. So they're really compressing all these checks that people have accumulated into a single one. So now, let's see how we can use this. Yes, so how do you construct accumulation scheme? You know, snarks are very powerful, you can use them for this. So every argument ends up yielding an accumulator scheme where basically what you do is you just let the decider be empty and you just simply, the prover of the accumulator just proves each relation individually. And then the verifier just verifies the snark. But of course, this is very heavyweight. So we can actually show how to do this better. But first, let's go back on to how to build the IVC from accumulation. So the way we're going to do it is we're going to take the proof from before, and now we're going to split it in two parts. Now the proof will contain an accumulator and an accumulation proof. And now the IVC prover will run the accumulation prover, to both prove the valid transition and that the verifier of the accumulator verified that the previous accumulator was correctly accumulated. And I apologize, I'm using accumulation a lot of time in this talk because we don't have much better terminology. So now the verifier of the IDC takes the new accumulator and the proof and verify the transition was done correctly and verify that the accumulator was done, successfully verified. Okay. Again, sweeping some subtleties below the abstractions, but this is basically how this ends up done in practice. And you basically get the same benefits as we had before for recursive proof composition, with the main difference that now the accumulation prover only need to prove the verifier of the accumulation. And this can be much cheaper than proving the verifier of an argument. Further, now you have some trade-offs. Typically, the decider is not succinct, so here you don't have chip verification anymore. But turns out, for the application that I consider, this is not that important, because what you can do is just you can wrap the final result with a final snark, and then you recover all the good properties plus succinct verification. So, this is what was one application in which we do it, but accumulation is not just useful for this, it can be used in many other contexts as well. So, one example is there's been, let's call it a Cambrian explosion of verifiable virtual machines recently. These are these products where you can write a program in your favorite programming language. It that's compiled down to machine code, typically RISC-V, and then generates a succinct proof of the execution. For the same reason as Ethereum, these need to use IDC in order to reduce the memory requirements in practice. And the way this is done at the moment is using the first approach I showed you, this recursive proof composition. Using accumulation, you can get significantly more efficient verifiable virtual machine because you can pay lower recursion overheads. Other places where accumulation found applications is that in digital provenance. So for example, when you're trying to prove that some image was generated from a real camera, for example, and then was very manipulated by, I don't know, an editor, which is much more very relevant now that ChatGPT has gotten very good at doing deepfakes, all these samples. But this is not just what it's limited to. There's been a lot of work on how to use accumulation in practical context. Now, let me tell you a bit about what are the three ways in which accumulation has been constructed. So there are three main areas. Accumulation was originally introduced in the context of elliptic curves. So there's a very long line of work with very confusing names on how to construct accumulation from elliptic curve-based assumptions. So these are very nice. They end up, but they, for more silently for an application, they don't give you post-quantum security. The two other areas are lattice-based accumulation. This is a very recent line of work, which is very promising. But for both group-based and lattice-based, they have a bit of a drawback in that they are not. They have accumulation costs that scale super linearly in the instance size. The line of work that I want to focus on today is that of hash-based accumulation. So, as we'll see, hash-based accumulation. In here, I mean hash-based accumulation that relies only on the random oracle model, no other assumption. And here we will see that we can get plausible post-quantum security, linear accumulation cost, and a lot of flexibility in the term of the choice of the arithmetic that you have to work on. So, okay, well, I think you'll look at questions at the end, but so let me talk a bit about the results. I think we will not dive too deep into them, but let me just talk a bit. So, I'm going to do some notation. This is the polynomial equation satisfiability relation. This is a generalization of very common NP-complete relations, such as R1CS, CCS, and generalized R1CS. Doesn't really matter what it is. This is just the abstraction that we use for this. And let me tell you a bit about our result, which is warp. So warp is an hash-based accumulation scheme. So when you need to accumulate L instances of this relation and corresponding accumulators, it achieves the following properties. So the prover cost ends up being fully linear in the input. So essentially, the prover cost is this L times the size of these polynomial equations that you need to evaluate. So you need to know, you do only a constant amount more work than actually deciding the indices yourself. Further, you have verifier cost, which is succinct, and in fact, you achieve this number of random oracle queries, which is roughly optimal for hash-based accumulation schemes. This is quite nice because the random oracle queries end up being where the recursion overhead in accumulation schemes tends to mostly gravitate toward. Finally, the decider is also linear time, and it does the optimal amount of random oracle queries. The security holds in the pure random oracle model with no other assumption needed, and you actually get a lot of flexibility over like what field you can use. You can use whatever is sufficiently large. And in fact, if you are able to do a bit of trade-off with asymptotics, you can actually use whatever fields, even binary fields, to accumulate. So I'm going to skip a bit because I think I don't have much time. The comparison basically, we are hash-based. We are the only linear time prover hash-based which achieves the optimal random oracle complexity, together with the concurrent work named FAX. So I'll skip a bit of the technical part. I'll just go to the conclusion and tell you where you can find more. So I'm going to very painfully go through all these slides. Look how pretty they are. They're incredible. You know, I'm sure it would have been great, but we'll get there. Look at this. This is beautiful. This is it's been a long time. So let me go to the conclusion and a recap of what we've seen. Okay, so we started with the theorem consensus, and we saw how IBC and PCD end up being a direct way to solve some of the problems that they've been having. Further, we saw some other applications, such as verifiable virtual machine, which directly benefit from these primitives. Then after that, we shifted to how we wanted to construct IBC and PCD, and we saw that accumulation is a very nice blueprint to actually get very efficient IBC and PCD. Now, we saw some of the lines of work that go into creating accumulation, namely group-based and habit-based accumulation, and we focus on hash-based, which is the one that we construct. Now, you have not seen, but this hash-based accumulation, they are born from a beautiful area of information theoretical cryptography, namely that of interactive oracle reductions. And constructing work ends up reducing to constructing two of these interactive oracle reductions. And this is what our scheme is like. There's a lot more that I could not show. So to do this, we had to introduce this out-of-domain sample for general linear code. We had to introduce this twin constraint pseudo batching notion, this new notion of round-around soundness, which I think are very interesting. But luckily, if you want to hear more, my co-author William will be giving another talk on work, which will be focusing more on the technical part in Toronto, May 12th. So if you're interested, there are details on this slide. Thank you.
Thank you, Giacomo. Unfortunately, we're out of time for questions, but thank you so much for the talk.